on a high-tech manufacturing floor, a place where microscopic parts are put together with unbelievable precision, a silent crisis is unfolding. There's a critical failure moving through the system, and it's threatening the very technology that you and I rely on every single day. This is the story of that failure and the hunt for the invisible culprit behind it all.
Yeah, deep inside the assembly line, something is fundamentally broken. The process for making these essential microcircuits, the tiny brains inside our phones and computers, it's failing at a terrifying rate. Every single failure is like a ghost in the machine, a tiny flaw that puts the entire production at risk.
Okay, so there's this metric they use called first-time pass yield. It's pretty simple. It's the percentage of circuit boards that work perfectly right off the line. And right now, that number is critically low. We're not just talking about a few glitches here and there. No, this is a systemic bleed, one that's costing millions and grinding the whole operation to a halt.
The defects are microscopic, but the consequences, they are massive. So the big mystery is this. What is this invisible flaw? What tiny little error is causing this huge chain reaction of failures, threatening the tech in our pockets, in our homes, everywhere? To find our culprit, we have to go to the scene of the crime. But this isn't some dark alleyway. It's a clean room, the incredibly precise world of surface mount technology. This is where robots place components smaller than a grain of rice onto circuit boards before they get fused in place with molten metal. It's an amazing process called soldering. And believe me, the stakes could not be higher. Every single board that fails causes huge delays on the production line. Each one has to be reworked by hand, which costs a ton of money and time. And frankly, it often just makes things worse. We're talking about creating even bigger problems like delamination, where the layers of the board literally start to peel apart. This isn't just a quality problem, it's an existential threat. So when your enemy is invisible, hidden somewhere in mountains of data, you don't call a regular detective. You call in a specialist. A new kind of investigator who isn't looking for fingerprints but for statistical patterns. Because in this world, the truth is always in the numbers. And that specialist is a methodology called Six Sigma. Its mission? Total, ruthless efficiency. It throws guesswork and gut feelings right out the window and replaces them with hard data and statistical analysis. It is designed to hunt down the root cause of any defect and completely eliminate it. The goal is to get so good that you produce fewer than 4 defects per million. It's about as close to perfection as you can get in manufacturing. The Six Sigma investigation follows a really strict 5-step protocol. It's an acronym, DMAIC. Define, measure, analyze, improve, and control. Think of it like a systematic manhunt for errors, designed to make sure not a single clue is missed and no stone is left unturned. So the first phase of the investigation starts with the evidence. Investigators start grabbing all the failure data they can get their hands on from the assembly line. They begin to sift through all that noise, looking for a signal, for some kind of pattern that points them to the main offenders. Every detective story has that one moment, right? The discovery of that one key piece of evidence that just breaks the case wide open. Well, hidden somewhere in this mountain of failure data was exactly that kind of clue. The question is, what did it show? And the breakthrough comes from this Pareto chart. You can think of it like a police lineup for defects. And the data is practically screaming at us. 2 culprits are responsible for almost 94% of all the failures. The first is something called dry solder, which is basically a weak or incomplete connection. The second is shorting, where solder accidentally bridges 2 points that should never, ever touch. Just like that, we've gone from 1,000 possibilities down to just 2 prime suspects. Now, identifying the suspects is a huge step, but it's not the end of the story. Not even close. Now, the real interrogation begins. The whole investigation pivots from figuring out what is failing to understanding why it's failing. Why are these 2 specific problems happening over and over and over again? So this next phase is all about deep dive forensics. It's about meticulously tracing every single step of the process, every variable, no matter how small, to find the true origin of the problem. We have to find the source. So to map out their investigation, the team uses a tool that's basically an evidence board. They start categorizing every potential lead. Could it be human error, the man category? Or maybe a problem with the machines themselves? What about the materials, like the solder paste? Or could it be something in the method, the process itself? At this point, everything is on the table. But after some really careful analysis, most of these leads just run cold. The data keeps pointing back to one category, method, and specifically to the reflow soldering process. That's the big oven that melts the solder. So the investigation narrows its focus to two critical variables: the heating temperature inside that oven and the speed of the conveyor belt carrying the boards through it. We have now reached the climax of the case. The detectives know their suspects, and they've zeroed in on the method of the crime. Now they have to run a series of very controlled experiments to find the exact combination of temperature and speed, the thermal code, that will neutralize this threat once and for all. And this really gets at the insane level of precision you need here. The temperature has to be hot enough to melt lead-free solder, which is around 217 degrees Celsius, but it can't be so hot that it damages other sensitive components that can't take anything over 230 degrees. We are talking about a razor-thin margin of error to get a flawless connection. This table is the key. This is what unlocks the whole mystery. It's like a Rosetta Stone for these thermal defects. It directly connects a specific problem, like cold solder joints, which is a type of dry solder, to a specific cause, like inadequate time over reflow temperature. Using this, the engineers can finally pinpoint the exact moment the process is going wrong and correct it with surgical precision. The code is cracked.
So, with the root cause finally identified and the perfect thermal profile dialed in, the immediate crisis is over. But the investigation isn't quite done. The last and maybe most critical step is to make absolutely sure this problem is solved for good.
This is what they call the control phase. The new optimized process gets documented. They create standard operating procedures so that everyone follows the exact same steps every time. And most importantly, they put a control plan in place to constantly monitor the data. That way, if the process ever starts to drift, even a little, they can correct it immediately.
The work of our data detective absolutely paid off. That first-time pass yield number, it skyrocketed. The result was a dramatic, you can't miss it improvement in quality, a massive boost in productivity, and a huge reduction in cost. The factory was saved, and the devices we all use are now built to a much higher, more reliable standard. So, the case of the failing circuits is closed. But it kind of makes you think, doesn't it? As our technology gets smaller and faster and more complex, thousands of these tiny, invisible battles are being fought every single day on manufacturing floors all around the world. It leaves you wondering, what other microscopic mysteries are just waiting to be solved?